Hi, good morning. Today we are going to talk about something very interesting. This is lecture number 7 in the series on linear maps, but we are going to continue with the linear isomorphism. This is something which you had already seen. Whenever you have a basis in a paradoxical vector space, we have seen any vector v can be written as summation, let us say xi vi, where xi's are scalars. Okay. Then we want to look at the map B going to x1, x2, xn, the ordered n tuple. That is what we are going to call as a coordinate map. We want to understand that in depth. This will be very important. It's a very good example of linear isomorphism, as well as it will play an important role when you talk about matrix representations of a linear map. Okay, later. Okay, come join us. Let us share the screen. So let us start with the thing, finite-dimensional vector space. So let V be a finite-dimensional vector space or a field, yeah, possibly R. See, when I say B is a basis for V, okay, usually one writes B as something like V1, V2, Vn, where n is the dimension of V, right? But notice that there is already some kind of an order in the basis. V1 is the first element, V2 is the second element, Vn is the third element. But when I say it's a basis, there is no such restriction. Okay, let us try to understand. Let us look at something like R3, right? Now, with the standard notation, E1, E2, E3, this is a basis. Standard basis where E1 is, as usual, 1, 0, 0, etc. Right? Notice that this, as I said, is same as saying E2, E3, and E1. Also equal to whatever you want. E2, E1, and E3. And okay, as sets, none of them are distinct. Okay, they are all equal. But in this set, E1 comes as the first basic element, E2 comes as the second element, E3 comes as the third element. Whereas in this expression, I would think of U2 as the first element, E3 as the second element, and E1 as the third element, and so on. Do you understand? So we are want to make use of the word an ordered basis. What do I mean by ordered basis of V? You say if B is a basis, I set up a one-to-one correspondence. Suppose dimension of B is n, then I will set up a one-to-one correspondence with 1 to n. This is a bijection. Then whatever one corresponds to the element of B, I call it as V1. Whatever 2 corresponds, I will call it as V2. And whatever n corresponds, I will call it as Vn. Then I will write B as V1, V2, Vn. This means when I say this, when I consider B as an ordered basis, okay, that means V1 must be the first element, V2 will be the second element, Vn will be the third element. Whereas when I consider as this as a basis also equal to V2, V1, V3, etc. Vn. Okay. So when I say ordered basis, I am specifying which is going to come as the first element. And if you want a little more specific, I can consider this as an ordered n tuple in B cross B cross B. This is n times. So that collect this as a set B1 Vi 1 less than equal to I less than equal to n. This is a linearly independent set. And if you want, also spanning set, or it's a maximal linearly independent set. That is the same as saying basis. But there is nothing like order. You understand that? But okay, please spend some time. Look at my example for R3, you will have an idea. Okay. So if I consider this as an ordered basis, the first element is E2, Second element is E3. Third element is E1. Okay, keep that in mind. So I hope all of you understand what is meant by an ordered basis. Spend some time. So let V be finite dimensional, V1 to Vn, not a basis but is ordered basis. Okay, then given any vector V in V, I know I can write it as uniquely as linear combination of V1 to Vn with the scalars in the field. This scalars now I'll call it, instead of A1, A2, An or C1, C2, Cn, I will call them as x1, V1 plus xn, Vn, where xj are all scalars in the field, possibly R as usual. And these are all unique, as we know, because this is the basis. Do you understand this? Now, therefore, I have an obvious map. Okay, call it CB, call this as a ordered basis B, which is from V to Rn. Given any vector V, I have an ordered n tuple of real numbers. I'm sure all of you can guess what it is. What will be CB of V? This is by definition x1, x2, xn. If you want to write as a row vector, or if you want to write as a column vector, x1, x2, xn. So let us make it this. We think of this as column vectors. Do you understand this? So this map I call as a coordinate map. Okay, relative to the ordered basis. Okay, associated with the ordered basis. Associated to the ordered basis B. So we want to understand this map. So it will be difficult for me to keep writing CB. Therefore, let me call it just phi. Okay, CB is phi. Okay. So this x1, x2, xn are called the coordinates of the vector B. And notice that when I say xj is one of the jth coordinate, what does it mean? When I say this is the jth coordinate of V, what does it mean? If I write V as summation of x1, v1, etc., xn, vn, or let us say a1, v1, an, vn, then the coefficient of Vj, namely Aj, is nothing other than Xj. You understand that? Okay. So that these are the coordinate coordinates. Notice that we had already exploited this when you wanted to compute the dimension of a vector space. Right? Intuitive way of looking at the dimension and then constructing a basis based on the reduction is already explained in a different video. You might have seen it or watched it already. Okay. Right. So I want to say that this phi from B to R and C or R and R, if you write it as a row vector, this is a linear isomorphism. So this is an example of a linear isomorphism. So in particular, any finite dimensional vector space, okay, will be isomorphic to Rn if V is n is the dimension of V. Okay, that's what we are proving. We had already seen it. Do you remember? V and W have the same dimension. We have seen V is isomorphic to W. We had already seen this. But we are giving a very explicit thing here with R. Okay, so what is that I have to check? So I have to check if V and W are in V, then phi of V plus W is phi of V plus phi of W. This is what I have to check. As usual, I'll check one, show that phi respects are okay, addition or preserves addition, and scalar multiplication will be left as an exercise to you. Now suppose write V as x1 v1 plus xn vn and w as y1 v1 plus yn vn. Since v equal to this, w equal to this, therefore v plus w will be some of these two things, x1 v1 plus xn vn plus y1 v1 plus yn vn. But vector addition, as we know, is associative and commutative. Therefore, I can group terms together. This is y1 v1, this is x1 v1, so I can take these two things. So I will get it as x1 plus y1 times v1. You understand this? Or if you want, let me write it x1 v1 plus y1 v1 plus next will be xn vn, etc. Now I consider these two, then what will I get? Dot 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 plus xn vn plus yn vn. But that is equal to, again using properties of vector spaces, this will be x1 plus y1 times v1 plus dot 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 xn plus yn times vn. Now notice that therefore this v plus w is written as a linear combination of the basic vectors v1 to vn, and we know this expression is unique. Therefore, what will be phi of v plus w? That will be x1 plus y1, etc., xn plus yn. Do you understand this? Okay. But this is a vector in Rn. This I can again split it as x1 x2 xn plus y1 y2 yn. Write it as a sum. But what is x1 x2 xn? This is phi of x, phi of v, and this is phi of w. So we have shown phi preserves addition. Similarly, phi preserves scalar multiplication. Okay, you check this. We have seen a lot of such things, so I don't want to waste my time. So phi from V to Rn is a linear map. Okay, and it is 1 1. Why it's 1 1? Because phi of v equal to phi of w. That means, suppose I write again, keep the same notation. What does that mean? This means x1 x2 xn equal to y1 y2 yn, right? But when does this happen? If this happens, if only if xj equal to yj for all j between 1 and n. But that would means v, which is x1 v1 plus xn vn, is same as in place of x1 I can write y1. Therefore y1 v1 plus yn vn, but that is your w. Therefore I have shown phi is 1 1, and phi is on 2. Why? Now you give me any a1 a2 an and rn, what vector I have to consider? Yeah, I'm sure all of you know. Take v to be a1 v1 plus an vn. This is a vector of course in v, and what is phi of v? Phi of v is a1 a2 an. Therefore this is a linear isomorphism. So pause, review, and proceed. What we have shown now? We have shown that the coordinate map, once you give me an ordered basis, I have a coordinate map. What is the coordinate map? Take v, write it as a linear combination x1 v1 xn vn. Then to each v, I associate the ordered n tuple of real numbers x1 x2 xn. Okay, either you can consider as a row vector or as a column vector, but I would prefer as a row column vector. Okay, write it. So this map is what we call as phi, or the coordinate map. We have shown that it is a linear isomorphism. So this is a very important special case of linear isomorphism. Okay, I hope all of you understand this. Yeah, okay. Now we want to look at another problem which will be interesting for later purpose. Suppose I have this vector space B, which is again finite dimensional, and suppose I have two ordered bases B and B dash. These are ordered bases. Okay, remember, not ordinary bases, ordered bases. Okay, let us call this as B1 to Vn, this as W1 to Wn. Okay, then I have the coordinate map phi B, which correspond to B, and phi B dash This correspond to b dash. I hope all of you understand how this is given. If v is this, with respect to this, I will write as b as summation xi vi 1 to n, then phi b of v will be x1 to xn. And here the same way, v I can write it as summation, let us say yj, wj, j equal to again 1 to n. Therefore, phi b dash of v will be y1 over to yn. If you want the column vector, then I have to put a transpose. Okay. So with this same vector space, if I choose different bases, okay, different ordered bases, the coordinate maps will be different. The simplest, we will start with a very simple-minded example. Suppose I have R2. My basis, ordered basis is E1 and E2, and my other ordered basis is E2 and E1. You understand this? So this is your V1, V2, this is your W1, W2. So if you give me a vector V in R2, you have xy, let us call it xy, then it stands for x v1 plus y v2, and here it stands for y w1 plus x w2. You understand that? Make sure, because what is this? Y w1 is y into 0 1 plus x into 1 0. Therefore it is, the way I did is this. Okay, I just gave a very trivial example so that you should learn. So therefore what will be my phi b of the vector xy will be xy, whereas phi b dash of xy, what is it? Yx. Therefore, because the first coordinate is going to be y now, second coordinate is going to be x. Do you understand that? Yeah. Therefore, the coordinate map depends upon the order of the basis. It depends on the basis. Okay, because the ordered basis, if I choose a different ordered basis, the coordinate map will be different. In particular, if I have an ordered basis b and interchange the order of b to get another ordered basis b dash, then the corresponding coordinate maps phi and phi dash, that is phi b and phi b dash, will be different. That's what we just now saw, because the underlying basis is the same. Okay, and let's look at one more example, slightly little more. Same R2. Let me take now basis again standard E1, E2. This is a standard ordered basis. And for B dash, let me take it my W1 equal to E1 plus E2 and W2 equal to E1 minus E2. This is our basis. Okay, this is a basis. Is in fact, in a minute you will see that. So if I give a vector xy, I will just write it as a row vector, even though, okay, because it will take a lot of space. I'm just writing it, but if you want, you can put a transpose if you are uncomfortable. Okay, this is, I want to write as some u times w1. Now let me say a times b w1 plus b times w2 for a b scalars. Okay, I can solve for this. This is what a times w1 is 1 1 and b w2 is 1 minus 1. This is going to be a plus b and a minus b. So my x equal to a plus b and y equal to a minus b. Therefore, what does it mean? This means if I add x plus y equal to 2a, or a equal to x plus y by 2, and similarly x minus y, if I take, that will be 2b. Therefore, b is x minus y by 2. Therefore, what is phi b of the vector xy? It is xy. And what is phi b dash of the vector xy? The coordinate map will be this. Therefore, it's x plus y by 2 and x minus y by 2. This is the coordinate map with respect to this basis. Okay, pause, review, proceed. I will just give an exercise for you so that you get used to that. These are all very simple exercises. Do not feel afraid. The only way you will become very comfortable and familiar with these concepts is work out these simple-minded exercises. I had already done that, so I'll just copy it from my thing. Yeah. So my V is now R3, and of course B is, let us say, standard E1, E2, E3, and B dash is I have done for R2 or R3. Let me just check. I think I did something for R3, but here what I have is only R2, so let me stick to R2. Sorry. Okay. And this is, let us say, this is 2, 1 and minus 1, 1. This is the basis, right? Okay. Then you want to write this basis. Yeah. Okay. So what I will do, I will try to write E1, the standard basis 1, comma 0 in terms of this. Therefore, that means A times 2, 1 plus B times minus 1, 1. This gives me 2A minus B and A plus B. This is equal to 1, 0. So this says A plus B equal to 0 or B equal to minus A. Now the next one says 2A minus B, that must be equal to 1, but minus B is A, therefore 3A equal to 1, that means A equal to 1 by 3. Since A equal to 1 by 3 and B equal to minus A minus 1 by 3. You understood that? Okay. Yeah, all right. And what will I E2? Similarly, I can find E2. Okay, and find out what is phi of B and phi of B dash. Okay, I leave it as an exercise. Okay, good. Now let's look at a little more involved example. Example 3 or 4, because I can consider the last one as example 3. Okay, now let's look at V to be polynomials of degree less than or equal to 2. Then we have a standard basis for this, namely 1, x and x squared. Then I also have another basis B dash where it is 1, x minus a and x minus a whole squared, where fix a real number. Right? So of course, as usual, polynomials of degree less than or equal to 2 over the field of real numbers. If it's a different field, you have to accordingly take this. Okay, because there will be Puritans who want all such things. You should be aware of that. Okay, now I want to say this is a basis. Okay, again these are ordered basis. This is the first, second, third. This is the first, second, third. Now notice that x I want to write in terms of this new basis B dash. How will I write it? It's very clear, x minus a plus a. So I can write it a times 1 plus 1 times x minus a. Therefore the coordinates, okay, coordinates of f in B dash are a and 1. Do you understand this? Are you happy? Yeah. And let's look at what are the coordinates of x squared. Okay, coordinates of x squared in B dash basis, in the basis, ordered basis B dash. Now notice that, let us look at x minus a whole square. It is x squared minus 2xa plus a squared, right? Therefore, x squared equal to x minus a whole squared, okay, plus 2xa minus a squared. Yeah, I want to write this is x squared. I am trying to express x squared in terms of B dash. Therefore, x minus a whole squared, nice, because that is in part of B dash. But x is not. So what do you think I will do? I will write it as x minus a whole squared 2 into x minus a plus a into a minus a squared. Do you understand this? X minus a whole squared plus 2 into a into x minus a. So I have written it as linear. And then this is extra 2a into a, 2a squared minus a squared, therefore plus a squared. Therefore this I can write as 1 times x minus a whole squared plus 2a times x minus a and plus a squared times 1. Therefore what are the coordinates under x squared? Under 5b dash it goes to 1, 2a and a squared. I don't know why that thing came. Okay, these are the coordinates. Keep all these things in mind. We will come to put to use soon. Okay. Now I want to attend to the very general problem. Okay, pause, review and proceed. Now suppose V is a finite space and this is an ordered basis V1 to Vn, and B dash is another ordered basis W1 to Wn. Okay, therefore let us write phi of B of V. Okay, that's, remember, phi of B is a linear map from linear isomorphism of V to Rn complement, and similarly let me simply call it phi and phi dash. Are you happy? So this will be, if I write V as x1 v1 plus xn vn, then phi b of V is x1 x2 xn in R and C. And similarly phi dash of V, let me write V as y1 w1 plus yn wn, then that's going to be y1 y2 yn. Okay, so I want to introduce a notation. I'll denote phi b of V in a this is VB. What does that mean? Write B in terms of the ordered basis B, then you get a column vector. That column vector I denote by B. This is same as this. This are all equal. Do you understand this? Okay. All these are equal. And similarly, I will write by VB dash equal to Y1 to Yn. This is same as phi dash of V. So this is again same. So what is my thing is, if I know, if you give me a vector, question is this following. Given V and its, I will call it x coordinates, that is coordinates associated to the ordered basis B. Okay, so I will simply make it easy. Okay, given V and its x coordinate, okay, and given V and its y coordinates, that is letter B dash, is there any relation? Between xb and vb and vb dash, that is there any relation between x1 xn and y1 to yn? That's a question. How many of you understand this? Okay, so we will establish a relation and check it in our the 1 or 2 examples which you had already done. With that we will stop. Okay, let us start. Now let us start with V, right? Then therefore I can write, okay, Wj as a linear combination of V1 V2 n, and it's a unique linear combination. You understand this? But notice that I want to do it for W1 W2 Wn, therefore this is very not a good thing. It's better to use a double index. So we will write it as Wj equal to A1j V1 plus A2j V2 plus ANJ Vn. Notice that it says I am differing from the standard algebra practice. They will usually write as A11 V1 plus A12 V2 plus etc. But I am writing the other way around. I am writing A11 V1 plus this is I will write it as A21 V2 etc. Please note this. Note the indices. Okay, the way I am writing. Right? So what is W1? W1 is A11 V1. Next is I just want you to get used to that. We want V2, therefore it should be A2 1 because this is 1 stands for this one. And the next one is A31 V3 and so on plus AN1 Bn. Do you understand this? Okay, good. Right? And similarly, now let's do that. So start with the vector V and suppose its coordinates are y1 w1 plus yn wn. What do I want? I want to find the relation between y1 yn and x1 x2 xn. You understand? So I will do it. Now w1 itself I have written as linear combination of v1 to vn. Do you follow that? So I want to make use of that. Okay. So let me write it. I will write it as shorthand notation, but I will explain in a minute in case you are have problem. So let me write it as w j yj wj j equal to 1 to n. Okay. I switch on the light. Okay. Right. Now this I same as j equal to 1 to n yj. But what is wj? Wj I can again write as shorthand notation. It is a. What is that? A1j. J is fixed. This 1, 2, 3 and all. Therefore I should write as a ij vj. J. Okay. Sorry. A ij vi. Okay, let me write it here itself. This is summation a I j v I equal to 1 to n. Do you understand this? So let me write it again. So it is a I j v I equal to 1 to n. So this I can write it as I want to collect vi. You understand? Therefore, I can write it as I equal to 1 to n and j equal to 1 to n of a I j yj into vi. Okay. So if you're a BSc student, it will look like some kind of a manipulation, but you should be confident of what is happening behind the scene. So I will explain that. So let us look at the simplest case. Okay. Let us say that I want to write it as something. Okay. So what do I want to do? Let me look at. Let me look at a simplest case. So let me write it as 3 elements if you want, right? Let us say I have A11 V1 plus A21 V2 plus A31 V3. Okay, this is my, let us say this is my W1, right? Okay. Now what will happen? I will have similarly Wj. Wj will be A1j V1 plus A2j V2 plus ANJ Vn. Yeah, right. Now when I write this, what will I do? I will add Wn equal to A1n V1 plus A2n V2 plus ANN Vn. So when I add this things b1 times, you understand that? Let us say y1 times, y2, yj times, yn times. What am I doing? I'm adding only v1 coefficients. Therefore, it's going to be y1 times here and yj times here and yj times here. Do you understand this? So all the v1 coefficients, when I add, what will I get? I will get a11 y1, a121 y2. What will be the jth thing? Jth thing will be a, oh, there's a j here. Yeah, right. Okay, that's correct. So what is this going to be? A1j plus a1n times v1. Do you understand? I'm adding only these things. Let me just circle. We are adding only these, the first column. You understand that? So how will I write this as a shorthand notation? So this will be the coefficient of v1. The shorthand notation I will write as summation. What is missing? A, I, because this is varying, and this will be 1. ai1 and yi. Okay, I equal to 1 to n. Do you understand that? ai1 yi times b1. And what will be the nth element like that? Again, I am going to multiply this by y1, yj and yn. So that will be, what will be? A31 y1, anj yj, an n yn. Therefore, it is again of this exactly the same form. ai n and yi I equal to 1 to n of bn. Do you understand? So this is what you have written. So this is, now this is summation over I. Then what will I do? I will take that out. Okay. Are you following? Okay. So spend some time and pause, review and proceed. So what you have found out is, so let me just write it quickly. So I have yj, wj, that is equal to, I'm just practicing so that you will also know, this is equal to over I, a, ij, vi, and this I am taking I out, therefore it's going to be j inside, this is yj. This is a, ij, yj into vi. But notice that this is a vector v. This vector has a unique expression, namely xi, vi. Therefore, I know what is xi. What is xi? Therefore, xi is summation a, ij, yj and j equal to 1 to n. So, what I have found now, given y, okay, y coordinate, we can write x coordinates. We can find x coordinates. That is, this is with respect to b dash, this is with respect to b. Okay, I can write it, but what are this aij? Go back. How did I get aij? That is by writing the vectors in b dash as a unique linear combination of the vectors in b. You understand? So, where, okay, where wj is summation a, I, j, vi, I equal to 1 to n. You understand? Okay. So I have now, we form a matrix. What is the matrix? The matrix A is aij. That is a11, a12, a1n, an1, an2, an2, ann. This is the matrix, right? Therefore, the phi b of v, which is the column vector vb, okay, is given by the matrix A times the column vector of b dash. That is, this is a11, a12, a1n, an1, an2, ann, acting on the column vector y1, y2, yn. Just make sure it follows. Yeah, right. Are you following? Are you sure? What will be x1? Just go back. What is your x1? X1 is a1j yj. Do you get it? X1 will be a1 1y1, a1 2y2, a1 n1. That is aij yj. Do you get this? Yeah. I take I equal to 1. What will I get? Summation a 1j yj. J equal to 1 to n. Okay. Now go back to this. Do I get it? Multiply this. I get it. Okay. So on. So let me just write it as a shortened notation because we will use it later. Therefore, V at B is A at VB dash. You should notice that this is the coordinates of B with respect to the basis B. These are the coordinates of B with respect to the basis B dash, where B, A, we know. What is A? We will give a name, we will use it. Okay. A is called the transition matrix. Okay. It is a transition from the taking from the basis B dash to basis B. That is, remember when I say basis, I am meaning ordered basis. Okay. So we will write it as A as B dash B. This means it's the transition matrix from the basis B dash to B. So what does that mean? How do I get the coefficients of A, the entries of A? Writing each vector in B dash as a linear combination of the vector in B. You follow that? So what will be my W1? W1 I wrote as A11 V1, next A21 V2. Do you see that? Yeah, did I do that? Yeah. A1J, 2J, and the A11 V1, A21 V2, A31. Okay. Therefore, that becomes the first column. Therefore, that is the jth column of this matrix B dash B is the coefficients of Wj in terms of Vi. B. The jth vector of B dash, you express it in terms of this. Then that becomes the jth column. Right? This becomes the first column. If I write Wj, go back again. Yeah. A1j, A2j, Anj. Therefore, that in the matrix, this will be the jth column. Okay. Please do not get confused. Revise this. Okay, at least twice. You will feel comfortable. Okay. Please go through it. If you want, take a pen and paper. Do it on your own. Don't lose heart. Okay. So let us just test it. Okay. Let's look at one of the examples where our B was R2, B was E1, E2, and B dash was, let us say, E1 plus E2 and E1 minus E2. Then what did it say? Okay, we found out XY was equal to, I do not remember, but if I remember, it is X plus Y by 2, etc. Yeah, X plus Y by 2, x minus y by 2, right? That is your y coordinate. Okay, therefore the coordinates, suppose I call it okay, u and v, that is my vector v is instead of y I will write it as u times w1, this is my w1, this is my w2 plus, oh, this is again v comes, very bad. So let us write v equal to x dash w1 plus y dash w2. Okay, this is w, right? Then we found out x dash was x plus y by 2 and y dash was x minus y by 2. Now what did our say? What is the matrix A? Matrix A said take the first vector, write it as a linear combination of this basis, and those coefficients must form the first column. This is E1 plus E2, that is 1 comma 1, therefore it will be 1 comma 1. And take W2, write it as a linear combination of E1 and E2, that is going to be 1 comma minus 1. Do you understand this? So what is that I have to check? It said that the x coordinate, that is coordinate b dash, that is bb, can be got as a times b dash. This, okay, we want to check this. Yeah, let us check it. This is xy, okay, whereas this is 1 minus 1, 1 minus 1, sorry, plus 1, x plus y by 2, x minus y by 2. That is the your x dash y dash, the new coordinates, b dash coordinates. Therefore, it's 1 times x plus y by 2 into 1 plus this. Therefore, xy. This will be 1 times x plus y by 2, minus of this will be minus x plus y, therefore 2y by 2, that's why. So I got it correct. So verified. Okay. So let us do one more example, with that I will stop. So the second thing, let us look at where v was polynomials of degree less than or equal to 2. Then what did we find? We fixed a real number a and looked at basis b, which consists of 1 x squared and b dash 1 x minus a and x plus x minus a whole squared, right? Okay. Now what is the matrix A here? Matrix A is, look at the new basis, write it in terms of the old basis, that is 1 comma 0, and this yeah. So my A is going to be, take 1 and write it as 1 times 1 plus 0 times x plus 0 times x squared, and x minus a I will write it as what? Minus a times 1 plus 1 times x plus 0 times x squared. Therefore it's going to be 1 0 0 minus a 1 0 and x minus a whole squared. How will I write it? X squared minus a squared, sorry, plus a squared minus 2xa. Therefore it's going to be x squared, this is going to be a squared and minus 2a and 1. Okay, right. So a good idea maybe for you to check it. Okay, what do I get it? Okay, what do I want? So I want to get x squared, okay, in terms of x minus the basis b dash, right? You understood? So if I know the coordinates of this, I can do that. Okay, but I can also do the other way around. What I want to do, let me look at, okay, let us stop here because that may be a little more confusing. Okay, I hope you understood. Okay, now as an exercise, I wanted to look at this. In fact, I thought I will do it but then time may be running out, so I will just explain. So I fix B, an ordered base is B, another ordered base is B dash, right? Then let me look at the transition matrix A of B dash B and the transition matrix B dash B, sorry, transition matrix A, B, B dash. Notice that what does it stand for? It stands for, what is its jth column? Jth column is write the jth vector in B dash as a linear combination of B. Here, what is the jth column of this matrix? The jth vector of B, namely Vj if you want. Vj I am writing in linear combination of Wi's. Here I am writing Wj as a linear combination of Vi, and the coefficients form the jth column in each of the cases. Do you understand? Right? Now what do you think if I take this matrix A, B dash B and multiply this A, B, B dash? Okay, try to understand, make a guess. So this means your x coordinate, okay, I will simply write V, okay, B as x and B dash as y, then we know the x coordinate is A, B dash B, y, right? And here y coordinate is A, B, B dash x, right? Therefore I can substitute this A, B dash B into A, B, B dash of x, right? So I'm writing, this stands for what? V of B, these vectors and this product of matrices into V of B. But notice that any vector admits a unique expression in terms of B. Therefore, what do you think I should get here? You have a guess? I should get the identity matrix. That means this matrix is invertible and this matrix is also invertible. They are inverse of each other. Okay, it will be a very good exercise. Okay, if you want to really master whatever I have done today, this is the culmination point. Okay, please try, do not lose hope. Go through it once or twice. It's the best if you discuss with your friends. You will really appreciate this. Okay, you see that I can compute. Without computing, I said A B dash B multiplied by A B B dash must be identity matrix, and similarly other one. Yeah, it will be nice to check it really happens. I hope you do that. Okay, have a good day.